Hello everyone. Today we are going to discuss another important step in your machine learning model building process, which is evaluating models. My name is Sumudhu Tenukon and I am a data scientist. I will be helping you through these lessons to navigate your data science and AI career. In previous lessons, we discussed about AI, data and machine learning, how they are related to each other and the importance of data in machine learning. And then we went to some little bit of detailed discussion on math and statistics required for you to be succeed in machine learning career, as well as the programming. We are focusing on Python as a programming language in this lesson. So we discuss about several Python libraries which you can get help to manipulate data, to do data analysis work, as well as to data visualization. So we discuss like how we can use Python as a programming language to build machine learning models using libraries available with it. So today we are going to discuss how you can use. Before we are going to discuss the topic for today, which is evaluating model performance, let's recap what we covered so far. Previously, we discussed how to get data, how to understand data, how to analyze data in terms of exploratory data analysis, applying descriptive statistics, and then how to transform your data into machine learning ready format. So then we discuss how we can figure out the design approach. So whether this problem is a supervised problem, how we can solve it. And we went through some examples, some regression problems as well as classification problems. We trained several models and we did like prediction on test data. And today we are at a point to know how we can evaluate those model performance. So those the model performance metrics we will be discussing today will be helpful in tuning your model to gauge whether your model is performing better or worse for a given change you make. Okay. So then also this will be very helpful for you to convince your customer or user of this model whether your model is doing good or bad in the real application. Let's refresh our understanding on the machine learning models and how they are built. So this lesson is focused on supervised machine learning and how we are going to evaluate them. In supervised machine learning, for the model training, we are sending data, which we call observations, with known result. So from the observation, we can find features, and we can also know the known result, we can call it output or target variable or ground truth. So in machine learning algorithm is going to fit a model to match the features into the ground truth and producing a machine learning model. So that process we call training. That is the process of building a solution. So this involves data scientist or machine learning engineer or whoever is building this process. And then if we are consuming the model after we build, so the user can provide a new record in matching the same input variables in the training, and then the machine learning model can infer the result or output. So that we call a prediction, right? So this is the usage of a machine learning model. Discuss why we need to evaluate or test our machine learning models. Like any other product, we need to follow a testing procedure to make sure our model is working well or our model is working for the desired objective, to fulfill the desired objective, right? So three key questions I'm putting here. We can get answers from this testing or evaluation step. Is my model performing good or bad? If it is bad, we need to find out a way we can improve, or we need to discard that model. We have to rebuild things. If it is good or bad, we found out. So we want to find out how good or bad it is. We need to gauge it. So we have to get some number or some metric we have to use to gauge how good or bad. And then how we can improve it. So if we found model is good but not that good, means like it's matching the objective or need of that model, but we should be improving it. So maybe your customer is saying, okay, we need a little bit of more work to do to get this model in use for our need, but it's not bad, right? So like that, you need to find out, okay, how good or how bad it is. And then the last step is you can use that metric to know like how I can improve it. Means the metric can be useful to know when you are improving it with some changes, how that metric is going to change, right? So you can track that. So this is what we are going to learn today, how we can evaluate the model and what tools or techniques or metrics you can use to evaluate your models based on the model. It's the steps of building machine learning model. So we previously discussed several steps we performed in our examples in this lesson. And also I mentioned today we are at the step of evaluating the model performance, which lead to tune your model based on the performance metric you get. So how we can do that? So in the tuning process, we use the evaluation metric to track whether a model is performing better or worse for each tune step. Means like you're making changes to your model and finding out whether your evaluation metric or the measurement you are taking for the model performance is going to improve or going to deteriorate. So in the tuning step, probably you need to revisit your data analysis step or the data processing step. It means like, you have to create some more variables, you have to do certain transformations from your data, and then you have to go through maybe the design step or then the training step, right? And you need to train some new multiple models with different hyperparameters, and then predict, and then go back to evaluation step to see whether the metric get improved or not. So this process is a cycle. It's not like a one way. So you have to revisit previous steps time to time. Sometimes tuning may not involve changing any variables or any data columns you had originally in the dataset, but simply changing some hyperparameters. It will only be like training new models with different hyperparameters and then evaluating. That's why the evaluation is very important. Another use of evaluation is after you tune the model, if you get the model into a satisfactory condition to send to production, you may need to have a discussion with your client or the user of this model to show them, okay, how good this model performing to get their approval, right? So the model evaluation will also be important in deployment and also in the production. If you are selling this as a product, you need to code, okay, this tool we are building is predicting something with this much accuracy or this much precision. So we will be discussing about these terms in the coming slides. Before we start evaluating, let's discuss about how we can choose the correct problem to solve. So you may find different ways to solve the same thing, but you need to meet the requirement. So let's take the example of an ice cream shop, and the ice cream shop owner wanted to know uh, how the sales is going, and they wanted to build a machine learning model to predict how many ice creams can be sold in a given day based on the characteristics of that day. He provided you historical data for like 2 year period, and then you have that data. So based on that, you will be predicting how many ice creams sold. So now think about like what kind of problem this is from your previous lessons, and also try to understand what are the features. So as you see here, so we can take day of week, is holiday, whether it's a holiday or not, and the temperature of that day and the rainfall of that day as features. And then what is your target variable or the y variable you will be using? Ice cream sold you can use as your y variable. Now focus like from our using our previous lessons, what is your target column? So it's a numeric column, and it has a numeric value. It's a continuous like column. So obviously you will know now what we can build is a regression model, right? But think like what are the other options you have? What are the things your client or the ice cream shop owner can ask you to build in terms of your machine learning model? So he may have like few options. He may ask you to predict how many ice creams sold in a given day. Basically, it's predicting a numeric value. He may ask you to predict whether or not he will sell 1,000 ice creams or not in a given day, which is basically predicting a binary value. Okay? And then the option C will tell you whether you can predict a range of ice creams, count of ice creams you sold in a given day, right? without saying yes or no. We are saying, okay, today you're going to sell ice creams between 50 to 100. Instead of telling you an exact number or saying yes no answer, you are giving like a little bit of more information than the binary problem. You're telling today, based on the characteristics, you are going to sell between 100 and 150. Maybe ice cream owner don't want to have that precise number, but the range in that case, the option C will be very useful, right? So now you see like different options you can have for the same data set and for the same problem, but you have to have like a thorough conversation with your user or your customer, whoever like you're building this model for, to understand that. So before going to evaluation, make sure you follow these things we learned previously, and make sure you have a very good understanding of these questions. What are my requirements, what are my data, what are my data types. Those are very important even in the evaluation step. So that's why I wanted to refresh this in this lesson. Okay. So yeah, if you understand your data, now you need to understand like what is your correct problem. So you understand whether it's a classification or regression. Let's try to refresh our understanding on different types of machine learning models, especially for the supervised machine learning models. So we basically have two main types, classification and regression. We had like plenty of example covered in these lessons. And the classification examples we can divide into two subclasses, binary and multi-class. So let's explore them. So in binary, it's very simple. Like we can predict yes, no answer, 1, 0, or you can predict one of two choices, only two classes. In multi-class, you can have more than two classes. That's kind of a increasing complexity of your machine learning problem, and also your model will be complex than the binary problem. Therefore, we need to explore a little bit. Assume you need to predict three different classes. In this case, let's assume you're predicting a color, just for example, blue, orange, and purple, right? And you have like two ways of building models. So in one approach of building multi-class models is building a series of binary models to make predictions and get the total prediction of the all models and combine into one prediction output. There are two ways we can do it. So we can build like one called one versus one. So which essentially you will be building, you will be training binary model for each pair of classes. You're taking pairs of all possible outcome classes. So in this case, we have three colors. You're pairing two colors each, and you're building three different classifiers, right? In this case, if you have n number of classes, you have to build n to n multiplied by n minus 1 divided by 2, right? So binary classifiers for the n classes. This process is computationally expensive, and also it's good for imbalanced data set, and it's also good for the kernel-based models, such as support vector machines. And in contrast to one versus one, let's explore one versus all. So in that case, you will be building models for each individual class. So still a binary model. You're building a model with one class versus all. So in the all means you are considering all other classes belong to like one class. And for example, blue versus non-blue, purple versus non-purple, orange versus non-orange, right? So the non-orange include blue and purple. And so you have to train a binary model for each class versus. And in this case, you are building n binary classifiers for n number of classes. And this method is used in models predicting probabilities, such as logistic regression. You can use that in perceptrons, right, like that. This understanding also very important. Some machine learning algorithms, if you are using scikit-learn, you don't want to choose which method you should use. Based on the method, they will configure by default. For example, if you are using logistic regression, they use like one versus all. If you're using support vector machines, you will be using one versus one. All right. So now let's come back to our ice cream shop problem. So now we know like the features for this data set, and if we are building a regression algorithm, so which column you should be using, or if you are using binary classifier, So you have to derive that from the data set, right? You can simply write a logic statement like yes, no, get the yes, no answer based on the count. And then if you wanted to multi-class classifier, if you want to build multi-class classifier, then you also can derive that different ranges using ice cream salt. So we did several exercises in our class, how we can do this kind of numeric value to a categorical column or binary column in Python using pandas functions. Okay, so let's try to revisit in our Python exercise for this lesson. But for now, let's understand this. So let's focus on the model training and evaluation again. So in the to know how the evaluation step is fit in. So the evaluation happen in connected to model training. Right? So after you train your model, like we saw in the flow diagram, so you will be training the model and fitting your test data set into the model and then evaluating, right? So this is connected to your model training process. And in this training process, this is a very important thing to know. So your observations or your input data set will be divided into two separate data sets. So which one data set will be using for training, the second data set you will be using for testing. So I will make another comment later, but we need to make sure those two data sets are not interfere each other. You cannot use training data set in testing or testing data set in training. Right? Same like if I'm giving you a quiz every day, and for your final exam, if I give you the same quiz, so that is not going to be useful to know whether you know this concept or not. So I had to give a different set of questions in your final exams than the daily quizzes I'm going to give, right? So in this training process, we will be using the training data set to train the model, and obviously it will going to build the model. And then after we build the model, we will be using the testing data set, which we keep aside in when we are splitting our data set into two. So that is what we are using for testing. So once we apply the testing data set in the model we build, and then we can predict output for those testing data. So that predicted output is now there. Now we need to find out a way how we can evaluate the model using that predicted output. Remember, so we get this testing data set also from the original observation set, which we had the known output for the ground truth also available in this data. Now what we can do, we can compare the actual value or the ground truth with the predicted value to know whether your model is performing good or bad. Okay, so we will be using a series of tools to do that. So that is we call like evaluating predicted versus actual. Right? So in every machine learning algorithm we will be exploring today, or every method we are doing, so this is what we are doing. We are predicting, we are evaluating the predicted versus the actual value. All right. So this is a simple example. Say like your actual value is 1. If your predicted is also 1, that means it's a successful prediction. It's a good prediction. And if your actual value is 1, if the predicted is 0, that means it's an unsuccessful prediction. Your model didn't capture that well. If your actual is 0, then the predicted is also 0. That is a good prediction, right? Like that, you can follow the logic. So your actual and when your actual and predicted is going to be matched, so that's a successful prediction. If not, it's an unsuccessful prediction. So this is we are going to quantify how successful and unsuccessful in using different methods in the coming lesson, coming parts of this lesson. So sometimes people do like 3 different data sets. It's optional. You can have like training, testing, and validation. Some machine learning algorithms will further divide your training data set into validation and training data set, and using the training data to build the model or do the fitting, and then do internal calibration of the parameters using that validation data set. You can also do like you can also have 3 data sets and do by yourself as well if you wanted to verify this more thoroughly, but make sure you do that only if you have enough data. So we will discuss that problem in the coming slide also. So few more important things. So no training data should be used for testing, evaluation, and vice versa. Right? So they should be kept apart. you should not interfere in one training attempt. So you have to keep the training and testing dataset kept separate or properly labeled in the same dataset. So you can either keep them as two different files or two different datasets, or you can keep in the same dataset, but you have to create a flag. Maybe you can say, okay, this is like testing dataset. So if this row belong to testing dataset, that is 1. If not, 0. 0 means it belongs to training dataset. Right? So you can keep in the same dataset, no problem. So you have to do train test split once once means like you cannot do train if you are building like multiple models, say like you are fine tuning the model, you should not try to split data into train and test every time when you are building a new model. So rather you can do this train test split as a one task, the task you do before you're starting the model building process, and keep the train test split throughout your model building process, means like do it while tuning and retraining the model. So you are using same training data set and same testing data set. So there will be little bit of problem can occur if you are doing this split every time when you are training the model. Therefore, it is very important to keep the training testing data in separate files or properly flagged using a new column. Okay, and for the training and testing, you should not use my if you get the data set of 1,000 items or 1,000 observations, you should not use first 7,000 as 700 as my training data set and last 300 as my testing data set. That's a bad approach. Instead, you can do that is split your training and testing data using a random method. So you have to have to pick that sample using a random sample. So if you are using Python and scikit-learn, there are like the functions available for you to do this task. You don't need to worry about writing all your own code or functions to do that. So there will be simple one-line code you need to execute in scikit-learn if you're using. Okay, so commonly used train to test ratio is 70% and 30%. So you can use 70% of your data for training and 30% of your data for testing. That 30% of data is what we are mainly focused in this lesson. So that's what we are using to evaluate your model. The second I had to make is about cross-validation. So that means if sometimes we don't get enough data for our machine learning model training process. So you need to have a large number of data to train like better performing model. Sometimes in the real application, we will get very few amount of data. We don't get enough data to train. So in that case, keeping training and testing as two different data set will be like problematic. Means like you will not see some of the feature combinations in the training data set, and you will not see some of the feature combination in the training data set in testing data set. Therefore, either your training or evaluation can be flawed. So in that case, you can have a mix of rows, but again, like keep the same principle. For one training attempt, you are using two separate data sets, right? But in this case, what we are doing is we are splitting data set into 5 different samples, or we can say 5 different sets. And so we call this method like k-fold cross validation. So k is 5 now, right? So split you can split your data set into k number of samples. That's why we call like the k-fold cross validation. And then what we are doing is at a given training attempt, we are using one of these like a sample as my testing sample, and the rest of 4 samples as the training sample, right? So in this way, you can see, as you see in the slide, you can create k number of configurations holding one out of k sample as the testing sample. So then you can use this one configuration at a time to train number of models. You will actually train like k different models, and you can take the average result, right? This will not violate the first note I mentioned about. You should not use testing and training at the same time, but in this case, you'll be using 1 out of 5 samples to testing at a time, and every time you are evaluating that, you are taking the model evaluation metric for each attempt, and ultimately you will be averaging the result. So the note number 3 is very important as well, no metric fit all problems and models. So you have to choose your model evaluation metric based on your business problem, based on the method you will be using, right, and based on the data you have. So it need to match your business objective, need to match your algorithm, it need to match your training approach, right? So select the, that's why I mentioned the select the best metric based on the, whether it's a classification or regression problem, whether it match your business use case or the objective. The note number 4 is selecting the best model out of number of models you build. In some machine learning attempts, we need to build several models. So we learn about hyperparameters. We can train models either using different algorithms. For a classification problem, you can use logistic regression, random forest classifier, tree classifier, for support vector machines, right? And you can train your models using different algorithms, but make sure you use same training data and same testing data, because otherwise your evaluation cannot be compared. Sometimes you need to use the same algorithm. If you choose, okay, this is the best algorithm I should be using, and but you can, what you can do is you can change your hyperparameters, right? If you are building a random forest model, you can control like how many trees you will be building and what some other parameters. Based on the parameter, your algorithm and how your prediction can be changed, right? So in that case, you have to use the same train and test data sets across all model training, and use the appropriate metrics. So that is very important. Uh, Sorry, the typo is should be metric. So the appropriate metric should be used to select the best model, right? If you are using accuracy, that should be appropriate for your business need and your application. If you are using precision, so we will discuss those things in the coming slides. So you need to use the most appropriate metric for each case. Okay, note number 5. The model testing evaluation should be part of the machine learning product you are delivering. So you're ultimately packaging your machine learning model into a product or embedding into an application. So your model evaluation results should be part of it. Any type of QA work. So you also need to provide this evaluation metric. Right? How good your model is performing is a very important question, not only to you, not only to the user, probably to your organization, or maybe a future developer who will be taking over this project and enhancing the product. So everybody needs to know your evaluation result. Therefore, try to preserve it and with some other things. So what other things is you can preserve it with the train test ratio and sample sizes, because in so data science and machine learning is a science. In science, we need to reproduce our result. So if I do experiment, if I get some result, and I have to when I'm reporting that result, I need to provide them. Okay, so this is how I did experiment under these conditions. I use these things to do this experiment. Then someone else, independent of me, should be reproduce that experiment and should be produce that same result. So in machine learning as well, you need to consider that if someone want to reproduce your machine learning model, they should be able to reproduce the same accuracy level or like same performance metrics. For releasing it with the model is also important. And during this process, make sure you have like a very good documentation and which evaluation metric you use, what are the hyperparameter values you choose to build this model, and what are actually don't have this in this slide, but what are the features you use, right? And these things also be well documented, so that will be helpful with the evaluation. Okay, and then and the deliver of a deliver or like a preserved training and testing data set to use for future enhancement. So it's also a good idea to keep your training and testing data set preserved for future enhancement, because sometimes after a month or after 3 months, your user or your customer will ask, okay, can we enhance this model? Some of the problems we need to resolve, some of the predictions are not going well. In that case, you cannot go back to your data processing, your data extraction, everything to do the steps from the scratch. Instead, if you preserve your testing and training data sets, you can simply try to adjust some hyperparameters or adjust some variables and retrain your model to solve those issues. So this it is also a very good tip to preserve the training and testing data. Okay, so this we already discussed why we are evaluating models. By now I think you should have a better understanding like why we are doing it. So let's explore how we can know whether our model is doing better or worse, or good or bad. Okay, so we discussed like two main types of models in supervised machine learning algorithms. So classification and regression. So you cannot use the metrics we use for classification for regression and vice versa. For the classification, we will be discussing metrics such as accuracy, precision, recall, F1 score. And also for regression, we will be discussing mean absolute error, mean squared error, root mean squared error, and coefficient of determination. Sometimes we know as goodness of fit. Okay, so we will explore one by one. First, let's try to explore what are the methods available for to evaluate classification models. Remember, in classification, in most algorithms, we predict class, predicting a class based on probability. Right? The classification is predicting a class. Some algorithms will be using different methods, but mostly it will be based on probability. If the higher the probability, it belongs to that class. Lower the probability, it will not. So three methods I can group or I can based on the similarity of the metrics or the methods we will be using. We can use like the tabular methods such as confusion matrix, probability, quantile table. We can create for the scalar values we can get from your the differences between ground truth or the actual versus prediction, which is accuracy, precision, recall, and F1 score, like we saw in previous slide. And the visual methods we can quickly visualize how good your model is performing is a receiver operating characteristic curve. In short form, we call it ROC curve. And the ROC curve can also provide a scalar value called area under ROC. We will discuss that. And the precision recall curve, in short form, we call PRC. It also can provide you another scalar metric, the area under the curve. Under the curve. And also you can plot a sample mean versus predicted mean. We will discuss this in detail. So these are the methods we can be used to evaluate classification model. Now, since you have like multiple methods on screen, so now like take a pause and think. Okay, so we have different problems, so we have to use the best out of these for the problem you're trying to solve, or what I'm trying to solve. We have to choose the best one. So that's why our understanding of each and every method will be very useful. Okay, so before we are exploring the method, so let's now try to recap our familiar problem, which is we try to predict the name of the fruit, or whether given a fruit, whether this is apple or pineapple. I made the assumption in this world we have only true fruits, apple and pineapple, but there could be different varieties of apple, different varieties of pineapples, right? So then in our introduction to machine learning lesson, we created a model as a classifier. So based on three different input values or features: color, weight, and diameter. So if color is red, yellow, green, so that's the characteristics of apple. Color of like pineapple is yellow and green. Then we had the weight and diameter. So we gave some numbers. Based on those numbers, we try to draw the decision trees, how we can make the prediction, right? Just recap that lesson if you forget that. And then so based on those the model, assume like we build a model using these three features: color, weight, and diameter. Then the model should output for a given fruit you provide to that model. Model should output and say whether this fruit is apple or pineapple. So that's basically our expectation of that model. Okay. So then we learn how we can think of that model as a function. Your features, your color, weight, and diameter. In the previous case, in this example, you can think of the feature or the variable x as showed in this diagram. And the predicted value, whether it's apple or pineapple, will be your y variable. We call it target variable, or the prediction, or the ground truth. Ground truth is from your training data set, right? So your model will predict value of y based on the features you provide. That's how we can see the action of machine learning model in a very high level. So now let's see like two different prediction it can make for this same problem. So if you provide an apple, like a red apple, you measure, you see the color red, and diameter is 10 centimeters, weight is 180 grams. And then what your model can do is it can, based on these features you provide, it can predict as apple, which is a true and which is correct prediction, right? So you know this is a red apple, and model also predict it's an apple. And then you provide a slightly bigger yellow apple, and you provide color is yellow and diameter is 11 centimeters, weight is 280 grams. So this had like little overlap with the features of pineapple. So your machine learning model predicted this as a pineapple, right? So your model made a prediction, but is it correct? No, it's a wrong prediction. So the first one is a correct prediction, second one is the wrong prediction. So now our goal is to know whether how much correct predictions it will make, how much wrong prediction it will make. Like I said, in a previous lesson, the machine learning models are not perfect. So we should allow the model to predict, make a wrong prediction, right? If we can make it 100%, that is good, but we have to allow it to make like few prediction. But how much few is a question based on the business use, right? So we will discuss like how we can make that determination, like how what is the range we should allow. But in this case, in these two examples, one is a good prediction, one is bad. So what our goal should be in model training process, we should increase the number of good predictions and we should decrease number of bad predictions, right? All right. So now try to explore how we can quantify these predictions. Assume you have like 100 truths you provided to this model, right? And then so if you provide apple, if as you see in the diagram, you can provide apple or pineapple. So your task is to ask the machine learning model, it's a simple question, this whether this fruit is apple or not, right? If it is apple, it will say yes, or answer is 1. If it is not apple, so it will say answer is no, or value should be 0. As you see in the table, the actual like value is apple. We provided an actual apple and then predicted as apple, which is 1, and we provided a pineapple predicted as 0, which is also true. It's not a pineapple, you should get the answer 0, and we provide apple as 1 and pineapple, like we have like a desired answer, right? Assume like there could be like at least one answer apple can predict as 0. So is the question is apple, if the answer is 0, it's not going to be a good prediction. So these predictions we can tabulate to quantify. So how many good predictions, how many bad predictions we can tabulate in a table below. So here, so I will be using rows to indicate like actual result or the known outcome or the ground truth, right? Actual positive means is apple is true. Actual negative is apple is no, means that it's not actually an apple. The positive means it's actually an apple, right? Let's focus on the orange the columns in orange color. Positive means our classifier is saying this is an apple, right? The blue is saying blue indicates whether this is apple or not in the actual or the ground truth. The predicted the columns will indicate whether it's what our model tells you, right? Sometimes it is an apple, the model may tell you it's not an apple, right? The positive is model tell you it's an apple, and the negative says it's not an apple, right? So we in this sample we have like 50 positive actual apples and 50 pineapples, right? So not apples, and 48 of them. So let's focus on the first row and first column. So 48 out of 50 apples were identified by your model as actual apples. So that's the positive. So we call it true positive. And then the second value in that row, first row, actual apples, two of them, your model tells you they are not apple. Like I said, your model is not perfect, so they can tell you, model can tell you they are not apple, but they are actual apple, right? And then let's focus on the second row, the negative row in the actual part, right? So we had one apple, we one not an apple, but your model tell you it's a positive or it's an apple. It's a wrong prediction as well, right? And then the second value in the second row, we have like 49 non-apples, which are not apples for sure, and also your model tell you they are not apples, right? So that is like a true negative. So it's a true negative is, your model also predict it is negative, they are actually negative, right? So if you focus on this diagonal of uh, this table or this metric, you can see those are the true predictions, right? So positive case as positive, negative case as negative, they are true predictions. In off diagonal, so you see like 1 and 2, negative as positive and positive as negative, they are wrong predictions, right? So we will this is how you can quantify and tabulate the results of the classifier. All right, so we will get to know about the terms which we can call each of these cells. You see here in this table. So we call it confusion matrix. So we will get to know about confusion matrix in the coming slides. Okay. So now let's think. Previously we had like binary problem. The question is asked whether it's apple or not. So now let's think that problem you wanted to make it a little complex. So now you wanted to identify the actual fruit from multiple fruit types, right? So we have like 4 different fruit types. Maybe this world or universe got like 4 different fruits now, not 2 fruits. And out of that, you wanted to build a classifier to identify which fruit is this, given the same measurements we make earlier, right? And then the same convention, the actual values are in rows and the predicted values are in columns, right? So if it is, just say, apple, if you give actual apple, and then your model also predict apple, so that is the true prediction. Same as that you gave like actual pineapple, and then you have in the column pineapple, you have like 45 of them are correctly predicted. Same for the strawberry, 46 strawberry, actual strawberry predicted as strawberry from your model. Banana, 49 actual banana was correctly predicted as banana from your model, right? If you focus on the last column, you will see like this is a well balanced problem, because this is like a made up problem. So for this model, you had like 50 from each fruit type. We provided 50 from each fruit type, and then that's how we wanted to know how the model perform, right? All right. So if you see in this table, there's the result. So apple predicted as apple, pineapple predicted as pineapple. This is the wrong prediction. Apple predicted as strawberry, banana predicted as pineapple, wrong prediction, and strawberry predicted as strawberry, right? The wrong prediction, let's explore 1 or 2 wrong predictions. So apple predicted as strawberry. So the true value is apple. So we provided apples predicted as strawberry. So this is that, okay? And then banana predicted as pineapple. Banana, this is the actual value, and predicted as pineapple. This is it. So like that, the all off diagonal values in this confusion matrix will be wrong predictions. All values in the diagonal are correct predictions. Okay, so this is what you need to understand. So let's explore this in a more systematic way and with the proper terms. So this is we call confusion matrix. So let's explore what is confusion matrix. The confusion matrix shows the level of confusion a classifier or test can make when making a prediction, right? So it's not about like how confused you are or how confused you by this matrix, right? So it's about like how confused your model when making a prediction. Right? Keep that in mind. So a few terms you wanted to identify. Condition is positive, so that we call P, means so that's how, like, your model will tell it's a positive case. So not, it cannot be, may not be actual positive, but your model will tell, okay, so this row belong to a positive case. And condition is negative, so you can your model can say, okay, this is negative, right? And P and N indicate like how many positive cases and how many negative cases from a given sample, and also from your model prediction. Like we discussed, like let's explore the terms like true positive, true negative, true false positive, and false negative. Right, like you see in this diagram, you can see in green there are like good predictions. In red, false positive or FN and FN false negative are bad prediction. Right. So like I said, if the actual value is positive and your model is also predicted it as positive, we call it true positive. That's a good prediction. And when the actual value is negative and your model is also predicting it as negative, we call it true negative. It's a good prediction. When the actual value is negative, if your model is saying positive, it's called false positive. And when the actual value is positive and the prediction is negative, we call it false negative. Few important relationships you can make: true positive plus false negative should be equal to the number of positives in your actual, and false positive plus true negative should be equal to total number of negatives in actual. So this I need to modify a little bit. So in the column, like P and N should be P actual and N actual, and the column total should be P predicted and P N predicted, right? Okay. So and also total predicted and total true positives and false positives. The addition of true positive and false positive should be equal to positive predicted total number of predicted positive values. Okay. Like two important things I wanted to tell about confusion matrix. It's not evaluation metric by itself, but it can be used to derive other metrics. The terms of the confusion matrix we can use to derive other important metrics to evaluate your model or to gauge your model performance. Okay, keep that in mind, and if you want to do a revisit, so make sure you revisit the terms of this true positive, false negative, true negative, and false positive. These are very important to identify. We will discuss with examples. Therefore, you will get more chance during this lesson to understand this. Okay. So the confusion matrix, using the confusion matrix, you can derive many other metrics for your model evaluation. So we will be discussing few today in this lesson. So, but if you go to this Wikipedia link, you can find like the definitions and uses of each and every metric you can derive from the confusion matrix, right? Okay. So let's explore like the few we intended to discuss today. First one is accuracy. So accuracy will tell you number of correct predictions over total number of predictions you make. Like I said previously, the true value, true positive and true negative, which are good predictions over total number of predictions you make, is your accuracy. Right? We will discuss this with numbers in the coming slide, but let's focus on the definition first. Then let's look at the precision. So, and also we call it positive predicted value, or in short form PPV. So the precision is also important thing in depending on the business use case. It will tell you if you predicted some amount of records as positives, what is the number of, what is the ratio of the good positives from the total number of predicted positives, right? So how we can get that number? True positive divided by total number of positives from your model, so which is equivalent to true positive plus false positives, right? So total number of predictors, true positives divided by total number of positives is your precision. Precision is very important to know, like, okay, how precise your prediction is. So, right, so if you make a prediction, how good how reliable it is actually, right? Then the recall sometimes we call sensitivity or hit rate or true positive rate, in short form PPR. How we can get the true recall is true positive divided by total number of positives in your data set. total number of actual positives in your data set, if I say very correct, right? It's true positive divided by total number of actual positives. So why recall is important in some business use cases? If you wanted to build a machine learning model, not to lose any good records or records intended to detect. So you have to have like a higher recall value. You need to have like all of the records you intended to flag as positive should be in the true positive set, okay, in this confusion matrix. Okay, then the last one is F1 score. Before we're going to discuss that, so the accuracy, precision, recall, they have their own disadvantages of using them alone. So sometimes you need to combine them together. So we will discuss like a case against accuracy in a coming slide. The precision and recall is highly tied to your business objective. But if you wanted to get some overall picture of your model, you can get the harmonic mean of precision and recall, which we call like F1 score. And then the harmonic mean, you can find the equation in the literature like you have below. And the harmonic mean is sensitive to the detection of positive and negative classes. So if you get a like F1 score for your model and you change the definition of your positive and negative, probably you will get a different F1 score. Therefore, that's why I mentioned it's sensitive to the positive, which class is positive, which class is negative. If I simply bring that idea again, we can say okay, if you're thinking of like some problem, you're saying detecting a disease is a positive case, right? And then you can build a model or classifier it, you can get a F1 score. And then if you are changing the definition, but not detecting the a disease in a person is a positive case. So in that case, your F1 score will not retain the same, it will be changed based on the definition of your positive and negative class. Therefore, you have to pay attention to that, right? So we'll have a detailed discussion in the coming slide. Okay, so have that in mind, the precision and accuracy. So, so few other things I wanted to highlight. Your total number of prediction is we can get p plus n here, and the total in the accuracy. So in the accuracy, so what we are trying to do is, if you are tracking accuracy to improve your model, is to uh, improve number of correct predictions. So my marking is incorrect in the top part. So you have to this red circle should go on the TP plus TN. So your goal should be to increase number of correct predictions, and also so total number of predictions should be the constant, right? So you have to understand that. So number of correct predictions will make increase true positives and true negatives. That's the goal if you are tracking accuracy. The goal, if you are tracking precision, your goal is to decrease number of false positives, right? So if you see in the left bottom corner, so the number of like false positives is 1 in this case. So you have to decrease number of false positives in order to improve your model performance, right? Because true positives, increasing true positives also good, but that will not help you to improve the precision. How you can improve the precision is decreasing number of false positives present in your result. How we can improve recall to be a better model is increasing number of true positives. When you increase number of true positives, you will be increasing the recall value, which means you are retaining all the good values from your data set. But when we are doing that, we may have to compromise the precision. So we will discuss that in later. So that's your model improvement is a balance of these two. The F1 score will combine all these two together and give you a metric. So let's try to compute these with numbers for the example we have in the slide. So if you take the accuracy, you know I don't need to repeat like true positive, false negative, false positive, and false negative in the metric you have metrics you have in the confusion matrix you have in the slide, but you can follow the numbers. So we can calculate the accuracy for this result, the confusion matrix. From this confusion matrix, the accuracy is 0.97, right, for this classifier, and for the precision we get 0.98. And recall we get 0.96, right? They are close to each other for this this example, but sometimes they can be different, very different. And then F1 score, if we compute, it's 0.97 for this example. So we can compute, you can follow the equations you had in the previous slide. Also I have them in this slide, and put the numbers in, and you can also compute these numbers by yourself. So try to do this as an exercise if you want to understand it properly. Okay, so now we know for the different metrics we can use. So which metric we should use then? Like I mentioned multiple times in this lesson, which metrics you should be using depends on the business use case and the objective, right? So let's take two examples. Let's take spam email classifier, so or filter. So we intended to do is, if you receive an email to your mailbox, your classifier should classify that email as spam or not spam. And if it is spam, it should move into spam folder. If it is not a spam, it should retain in the inbox, right? So that's basically what we do. So few things we wanted to know, like, okay, if you wanted to build a classifier, so what are the most important thing we should track? So if you're a user, we all consume email, so do you mind having a spam email in your inbox, or do you mind your good email in your inbox move to your spam folder and eventually get deleted? You can lose some important information, right? So therefore, what we need to focus in as like a spam email filter, like a classifier, we should not flag good or important emails as spam, so which may lose user some important messages, right? And also the second thing, even if we do that, we need to also focus our modeling method not to miss a spam email, right? So if you are missing a spam email, to flag it, and then you are delivering it as a good email, probably it can contain a virus or a harmful link, or your user can get into trouble. So you should minimize that as well. But what is the most important thing for a user? You can ask that from the user. That's why you need to have a domain understanding or the good understanding of the business use. So this answer you should get from the business user. And if they said, okay, I don't mind having a few spam emails in my inbox, but I should not use important email, falsely flag as a spam, right? If you're running a business, so you may lose a very important business. So in that case, spam email filter, the most important thing for the spam email filter is not to flag good email as a spam, right? So what we should focus at, we should focus minimizing the false positives, or we should focus on the precision, right? If we say a spam, so that should be like, precisely it's a spam, right? We can have like 1%, 0.1%, like saying wrong prediction, but majority of them should be, if you say spam, should be into great accuracy, should be very precise, it should be a spam. So let's take another example. So think of a medical diagnostic. Say we are trying to check a disease, or like do a test on your patients to find out whether this person is having this disease or not. So in that case, what can go wrong if we don't make the prediction correct, right? So if you are saying, okay, I'm predicting like a disease, so if the patient is actually infected, if your classifier is telling, okay, the person is not infected, what is more dangerous? So the person you are going to send home, that is more dangerous, right? If it is the disease, it can be spread like the COVID. So that person can meet other people, go home and spread the disease to many people, because your classifier said the person don't have the disease. That is a very dangerous situation for a medical diagnostic. So we should focus on false negative in that case. If the person is positive, actually, if you say he's negative, he or she is negative, then that's a more dangerous prediction you make. So therefore, we should focus on reducing number of false negative. Here also we should focus on the second one, should not flag non-infected person as infected. Say you don't have the disease actually, but your classifier is telling you, okay, you have this disease. So what implications you will have? You will probably like feel a little bit of uncomfortable situation, right? So like the first one is for the spam email. I forgot to add the animation. The first one is for spam email. So you have the false negative, which is bad as well, but the more bad is the having a lot of false positive. So in the medical example, so what you will have is if you are classifying a person, the truly infected person as positive from your model, that you can get proper medical treatment, right? So that's a good case. And if you are classifying like actually negative for that disease, a person, if you don't have the disease and also your model is telling no, so he can go and he can meet other people, he can do whatever he wants. So because he don't have disease and also your model said no, you don't have disease. But if you're in the other case, if you say your model say yes, that person can go and spread that disease to the community, right? So the burden of a person who don't have the disease, which is the negative actual case, but your model falsely predicted you're a positive case, which is false positive. The burden is on the person, but the impact on that from that person to the community will be less, right? So therefore, based on your application or business objective, you need to choose whether you should focus on precision or recall. And we will discuss how many like ways we can do. So now let's do a small exercise. Let's do some thinking. So now, based on the two examples we discussed, let's try to answer this question as well. So think of a credit card transaction fraud detector. So you have a machine learning model to predict whether your credit card transaction is a fraud or not, right? So what that model does is it will collect the transaction details. So you can think of the details will be collected: your address, your name, and which IP address, if it is online transaction, which IP address this is coming from, and which country, which location, right? And if it's a shop, the location of the shop and merchant name, etc. Like so, and what is the transaction amount, what is the transaction time, right? So few things you can even think of like some red flags, right? If the transaction happened like 1 hour past midnight, or like if the transaction happened in a location or a country very different from the card owner, so those things kind of red flags, right? All of these taken into account, and in your machine learning model, it will decide whether this transaction is a fraud or not. If it is if your machine learning model detected it as a fraud transaction, what it will do is it will trigger like alert system, and it will send an alert to the user or the card owner. So then card owner will get to know if like his or her card used by like another person without knowing, or maybe that person's card is lost somewhere, and so he's trying to find it out, but meantime someone took the card and make a transaction, right? So in that case, he get the alert and he can take the necessary action. So file a police report or talk to the bank or the credit card issuer and stop the transaction. So he can get the alert. So that is what your machine learning model does, right? If it is not a fraud, so your model detected based on the characteristics of the transaction, your model said is predicting this is not a fraud. Model can simply ignore and no alert is received, so everything good as usual, right? So this is what the problem. So now the question to you is, as person, think of like you are the person who is owning the card, what you should more concern or more care on, right? So if you're a person who is building this model, what should you more care on, with the precision or recall? So let's answer the first question from the user perspective, right? If you're a user or the credit card user or the credit card owner, you are receiving emails or text alerts for every transaction you do. You are purchasing something for like few cents, so still you get an alert. You're purchasing something for $1,000, you still get an alert, right? So every transaction you make, if you make 100 transactions per day, it's unlikely a person do that, but say like you do that, you get 100 emails or 100 text messages. Do you mind that or no? If you say like if you mind that, so that means you will lose some important features. So let's see why. So if you are the credit card user, think like your credit card is stolen and someone did a transaction and you never even noticed, and also you didn't get any alert, right? And then you keep the business as usual and your credit card is getting more and more transaction, you don't get any alert, so your money is spent by someone. That's the problem. Which one you worried more? I think most of you worried about the second one, right? You don't mind getting an additional email or an one plus text message, right? So that you're more worried you're not getting any alert for the actual transaction. So let's look at the confusion matrix with that understanding. So now let's put our feet on the machine learning model builder shoes. Okay. So now which one we should focus on? If a fraud transaction occurred, right? There is a positive case for fraud, actual fraud, and our model should predict that as a fraud transaction. That's the good thing. If it is a fraud transaction, if our model said no, it's a good transaction and let it pass through and no alert is generated, that is a very bad case. Okay, so that is what you should worry as a credit card owner, right? If the transaction is not a fraud, but the model flagged as a fraud and send an alert, so you get some annoying alerts from your credit card, that's a false positive, but you would not worry too much about it. You can simply ignore that message or contact bank, but you will not lose anything as a credit card owner, but that is a false positive. So now let's focus on the question. So which one you should be more worried on? So you should worry on re reducing number of false negative than reducing number of false positive, right? The recall is what you should be focusing on. Okay, so if I put animation here, so the good cases, you will be happy. So you're not getting any alert, you're getting an alert, right? You're getting an alert unnecessarily, but you're not too worried. But the time you should get an alert, so fraud happened, you don't get an alert, you should be angry and you should be worried very well, right? So that's what so like that, if when you get a machine learning problem and you are thinking of the evaluation, you should always think of okay, these things, whether you are tracking the problem correct. That's a part of evaluation, not only the metric. So you need to understand that well. Okay. All right. So now let's look at like one other example. So this I call a case against accuracy. Sometimes accuracy is not the best metric you should be tracked in machine learning. So especially in if your if your data set is imbalanced. So which I mean, like your positive classes and negative classes have like very different number of actual records, right? In this case, infected, you have like only 5 out of 100 are infected, 95 out of 100 are not infected. So it could be like a reality, right? So you don't have like a lot of infected people in the community for a given disease, right? You may have like a lot of non-infected people. So that is the reality. In reality, we get imbalanced data. Sometimes data is like highly imbalanced. Sometimes data is slightly imbalanced. You can have like 70%, 30%, or 20%, 80%. In some extreme situation, you can have like 0.1% is your positive class, and like rest of the thing is percent is your negative class. So we had to apply some special techniques in those cases, but this is also highly imbalanced sample. You have 5% for infected and 95% for non-infected actual, right? So now your model is predicted out of the 5 infected people, your model predicted 2 of them as positive and 3 of them as negative. So which is like a bad case, right? So you are telling a person who is infected as not infected, right? Not only bad, is dangerous to the community spread, right? So you can follow the confusion matrix from what we learned, and then let's calculate the accuracy first. So accuracy we will get 0.95, okay, for this model. And the precision, so we know how to calculate the precision from our previous slide, and the precision is 2 out of 4. So you have all like a 4 values you predicted positive from your model, and only 2 of them is actually positive. So you get 50% as your precision. It's not that good. And the recall you get 2 out of 5. You have actual 2 out of total 5 you had in this sample, right? So it's on the 40% or zero point 0.4 is your recall, which is also bad, right? So this example, your precision and recall both are bad, but your accuracy will tell you a different story. Accuracy will tell you, okay, our model is 95% accurate or 0.995 in terms of ratio. So can you sell this model? Yeah, probably if you are a marketing person, you wanted to sell like a bad product, if that is your professional habit. So you can say, you're saying, okay, this model is 95% accurate and you should buy it. You can put like a nice advertisement. But if it is actual in actual case, the mission as a critical application like this medical diagnostic, people in much more trouble by following your accuracy value, right? So 95% accuracy is not something you should trust in this case. Rather, you can trust precision and recall. Or like if you wanted to get the combination of precision and recall as the metric, you can use F1 score. So F1 score in this case is 0.44. All right, so that's we understood now the accuracy is not the best metric you should be using. Let's make a slight modification to our problem definition. Let's make not infected class as our positive class and infected class as our negative class. As you see in left bottom corner in the confusion matrix, now our true positive become not infected in the actual class, predicted as positive. So now what is our test is predicting as positive. Those are like who are not infected. Okay. Similar to that, people who got infected actually got a result as negative, that is the expected, because our negative class is infected class. So we have like 2 people out of 5 infected people predicted as negative. That will become our new true negative. Similarly, those who infected predicted as positive is our false positive under new definition, and those who are not infected got negative result from our model. Like 2 people got that result are false negative. So by changing this definition of positive and negative, we see the accuracy remains the same, but precision, recall, and F1 score all will change. So that tells us precision, recall, and F1 score is insensitive to the negative and positive definition we choose. Therefore, we should be careful of our positive and negative definition and should be connected with our business objective when we are presenting our result in precision, recall, and using precision, recall, and F1 score. So now let's look at like slightly different example. This model is another imbalance model, but this is a bad model. I will have some examples for the bad model later, but this will not predict any positive cases out of this model is simply a useless model. But how we can know that, right? So sometimes we don't know until we test it, right? So this is how we can get. So still it get 94% accuracy. Now you see the case against accuracy is very strong. This model will not predict anything good, right? Like anything good means like a negative as negative, at least it can be used to detect negative as negative, but it will not do the job we want to do. It's not meeting the business objective, right? But it's saying the accuracy is 0.94. And then the precision is 0. Basically, you don't have any true positives, right? The recall is also 0. You don't have any true positives. F1 score, you cannot, it's undefined basically. Yeah, so this is what you get. Previously, we learned F1 score is sensitive to the definition of positive and negative classes in your problem. F1 score considers true positive, false positive, and false negative into account when computing the value. It does not take the true negatives into account when computing F1 score. If you wanted to have a metric which is insensitive to the definition of positive and negative classes, you should be choosing Matthews correlation coefficient. In short form, we call it MCC. MCC will take into account the true negative when computing the value. Yes, you see in this equation, it will be a combination of all four different terms in the confusion matrix. Unfortunately, it is only available for binary classifiers. It cannot extend to multi-class problems. In these two examples I'm illustrating here on the right side, on the top example, you will see the infected as our positive class and the not infected as our negative class. And your F1 score, the same example we discussed earlier. So we got F1 score is 0.44. For the MCC, we get 0.42, taking true negative into account. And when we flip the definition of negative and positive classes, which makes the not infected as the positive class and infected as the negative class, we get F1 score, which is a higher number, is 0.97, but MCC remains the same. So this is an example showing you how the MCC is insensitive to the definition of positive and negative classes. Let's look at some extreme models, which are bad examples actually in terms of performance wise. And this will also help us to give some understanding of how a bad model can behave. So in this model, we send 100 records or 100 different observations, and so it will predict all 100 as positive. So in such a model, the contribution matrix will become true positive and false positive will take like the values, but the false negative and true negative don't take any values, as you see in the bottom right corner confusion matrix. Since all input values turn to be positive from the model, and the accuracy will become 0.5. So it has a sizable accuracy 0.5. And the precision will also be 0.5 because you have like all 50 positive cases will become positive, and also you will have another 50 as negative. So your precision is 0.5. Even this model performed not that good according to our common sense. It gives you the 100% recall, or the recall value is 1, because all positive cases will turn to be, all actual positives will turn to be positive from your model. So you covered all positive values possible. And F1 score is 0.67, so which is a high number because this is like predicting all positive cases as positive, and the true positive gives you the recall 1. But when you compute MCC or Matthews correlation coefficient, so that will be undefined because all the terms in denominator and numerator both are 0 divided by 0, which makes you get your undefined number, and so this will fail your Matthews correlation coefficient calculation. Let's look at the second extreme example for bad model, which is case number 2 in our lesson. So it predicts all input as negative. So no matter what you provided to the model, it will always say it is negative, which does not serve our purpose, but let's understand how the implication of the evaluation metric. So in this case, all actual positives are makes negative, and it's obvious the all actual negatives also turn to be negative as the predicted value. So the accuracy of such a model still be 50%. Remember, the accuracy won't change in this case because you have like 50 and in the negative, actual negative predicted as negative, that is a true result. True negative is 50, therefore you get accuracy is 50. And the precision of this example is undefined because there are no true positives and there are no false positives. Recall is also 0. The reason is that there are no true positives. And F1 score will also become 0, but MCC will become undefined. So this is like a model which will be not useful at all. Now let's look at some interesting example about bad model performance case. This model predicts opposite. If you send actual positive, the model will tell it's negative as a prediction. If you send actual negative, the model will tell that is positive. This could be simply something a change from the design, right? So the model will work, but your how you interpret model result could be flawed. So you probably need to check your coding or your model definition or how you interpret your results. This could be simply fixed, nothing wrong with the model training, but simple fixing the code as well, solving this problem. But let's examine this further. So the accuracy of such model is 0 because you don't have any true positive or true negative values. Precision will also become 0 because there are no true positives. Recalls the same. Due to no true positive, the value is 0. Hence F1 score is 0. But the interesting fact is MCC value will become -1. So this will be an indicator, like I mentioned about earlier. So you have to revisit your process, the post processing of your model result, whether you are interpreting your result correct, or there could be some simple fix in the code that you can get over with it. We previously looked at some metric we can use as a scalar values to interpret model performance or the evaluation results. So now let's look at some visual methods, and also we can combine those visual methods with some other metric. We can generate a scalar value to interpret model performance. First one is a receiver operating characteristic curve, which we call ROC curve, and the precision recall curve, we can call like the PRC curve. And the sample mean versus predicted mean is another method. You can plot the model result and get an idea of how your model performing with a good or bad result. So let's look at the probability cutoff. Precision recall curve. So in this example, we previously used to predict which fruit it is, so whether it's apple or pineapple. If the actual class is apple, it will say 1. If the actual class is pineapple, it will say 0, the actual value. So then when we send these, the variables belong to these fruits into the model will predict probabilities. Remember what I mentioned earlier, the classification models mostly they predict probability, and based on the probability we can decide which class they belong to. So in this case, let's focus on the first row. The first row will tell you the actual class is apple, actual value is 1, and the model will say the predicted probability is 0.85. And so we can use this predicted probability to decide whether this is an apple or not. We can simply take probability greater than 0.5, we assign the apple class. If it is less than or equal 0.5, we say it's not an apple. So in this case, row number 1 will be class 1 as predicted. If we change this probability threshold, so we can change the value. So we can give any threshold value. Now we can say, okay, I'm only telling from the model result if the probability value is greater than 0.9. If you add that condition, the result for apple or the predicted value for apple will become 0, which means the model will tell you it's not an apple. It gives you the probability as 0.85, but because of the threshold value you choose, you will get the class as not an apple class. Similarly, you can lower that threshold. If you use probability greater than 0.3 is your the threshold value, so any probability value greater than 0.3 will give you apple class. If it is less than or equal 0.3, will be non-apple class. So in this case, since I have the probability 0.85, you will get 0.1. So let's look at the second row. In the second row, you get probability 0, 1, 4. Under all three conditions, whether it's probability greater than 0.5, it fails because it's less, and probability greater than 0.9, it fails, yes. So then it will should get 0, and probability greater than 0.3, it will also get 0. So in this case, it's not an apple, it's not actual apple, and also it predicted under 3 threshold values, so it will predict it's not an apple. You can follow other numbers and other rows in this table. I will take like one more. Let's look at a different one, like the very last one in this populated rows. So the pineapple, its actual class value is 0. The predicted probability is 0.49, which falls under the first condition. So the probability is less than 0.5, which makes it 0, which is correct. So under the threshold we set, it will identify as not an apple. The second condition, when we consider probability as greater than 0.9, it will identify as not an apple. But if we make the threshold value as probability greater than 0.3, so in this case, it falsely identifies this as an apple because the probability is 0.49, but our threshold is 0.3. So in this case, we should be careful. So we get like a false result for apple, but the actual class is not an apple. Okay. So now let's look at the same thing in a diagram. Right? So in the right side diagram, you will have the x-axis will be the probability value you can take as the threshold. So let's say you are cutting off from any probability threshold value. So you will change the precision and recall. So if you take the probability of the first predicted probability greater than 0.5 column, right? So if you use that column to calculate your precision and recall, you will get a different precision and recall. And for the second condition, probability greater than 0.9, we'll get like a different recall and precision. For each probability threshold condition you apply, you should get different recall and precision values. If you plot them together by changing the threshold value, you will get a plot like the one you have in the right side of the slide. So the precision normally get increased when increasing the threshold. The recall value will decrease when increasing the threshold value. So that is obvious. You can check with the result from like what we have in our example classifier we did in the Python exercise. So we will be doing more in this class. But if you do that, you will find a similar curve. It will be slightly different, but you will see the same trend. Precision increase with the threshold value, recall decrease with the threshold value get increase. Right? So the threshold value defined, above that threshold, you will see the class 1. Below that threshold, you will see the class 0. All right. So let's look at our intended visual method we wanted to discuss. Receiver operating characteristic curve, which we know as ROC curve. This will give you a true positive rate or recall as your y-axis and false positive rate or fallout rate as your x-axis. So area under this curve we call AUC. So area under curve of ROC curve will be a metric you can track in terms of model performance. So what is the goal here? The AUC for an ideal model. For an ideal model, AUC should be 1. The reason is this red curve should cover the entire square if your model is ideal. Means you get all true values in diagram. All predictions either should be true positive or true negative. But in reality, we will not get that. Therefore, we should get a value always between 1 and 0.5 for this area under curve. If your red curve falls on the diagonal of this plot, which indicates your model is behaving no better than a random guess. Someone just giving you random guess of the result. Someone's randomly say whether this is a positive or negative. So that will not be a good model. So if your area under curve of this in receiver operating characteristic curve is half, which is your red curve is lying on the diagonal of this plot, will be like not a good model, right? So it's no better than random guess. So let's look at another curve, which is called precision recall curve. So which if you have precision as your y value and recall as your x value. Okay, so both these curves, you probably notice the value, the range of values should be between 0 and 1 for both axes. So in the precision recall curve, the green curve should follow a trend. The lower true positive rate or lower recall, you will have the higher precision. And when you increase the recall or true positive rate, you will reduce or you will compromise the precision. So in this example, you will see in the orange guiding lines. So you will see when you have a higher precision, you have a lower recall. In the blue guidelines, you will see when you lower that precision or you increase the recall, you will so you will lower the precision, you will get the higher recall. Or if you increase the recall, you will get a lower precision. And you can also compute area under curve for precision recall curve. In that case also, you should get a value less than 1. The higher the area under curve, both these methods will be a metric, a scalar value you can track. So if the value is higher, means your model is performing better. You can track both of these area under curve values, or one of them if you wanted to track as a gauge to know whether your model is improved or not. And also like how we compute this each of these curve values is the same way we discussed earlier. So each point in the both of the curves will contribute by different threshold probability value you choose to determine whether it's class 1 or class 0. So let's look at like some detail look at the tabular method as well as another graphical method we can use to determine whether our model is performing good or bad. In the right side, you have a table. So we learned about how we can generate a quantile from a numeric column in pandas in Python. So now think you created this quantile column using the probability value or the predicted probability value from the model result. You will have like a distribution of probabilities, so you can divide them into even buckets or quantiles. So in this example, we had total 6,513 samples in our testing data set. We predicted their probabilities, or actually this is coming from the income data set. We worked on this example during the class. So this was coming from the testing data set. So out of that 6,513 samples, we can divide them into even 10 buckets. And we can arrange them based on the probability value from lower to higher, and then we can set the cutoff value. First 600, roughly 650, or here it's a 659, and the second 646, like that. You can roughly, those are like even buckets we can divide into. So when we do that, so we can get like from the lowest quantile to the highest quantile. So we can assign a number, or we can leave the ranges of probability as the quantile label. Here I converted them to number. The lower the quantile number has the lower probability, higher the quantile number has the highest probabilities. Then the first column after the quantile column, you will see the mean probability. Since we have lower probabilities in the first quantile, the mean probability of the 659 will be very low. So you will see the 0.003, the predicted probability value. Similar to that, we can look at the last row, the row number 10 or the quantile number 10. The mean probability is 0.8 because we choose the highest probability result or highest probability rows in the test data set as the quantile 10, right? So now let's look at the bucket count. Bucket count is nothing but it indicates how many rows qualified under each quantile. And then the response count, you will see another the pattern from this table. The lower the quantile number, which is like lower probability rows, will have lower response count. Response count is nothing but how many positives from your model. So we have 4 positives from quantile number 1 and 540 positives in from quantile number 10, and you will see a gradually increasing pattern there. We can also calculate the bucket fraction, which should be closely similar in this quantile distribution, because we divided our testing data set into even number of bucket, even number of row count as much as possible. So you should have like a 0.1 as roughly 0.1 as your bucket fraction. So that is no significant in this table. But the response fraction will be how many responses per how many records qualified under this bucket. So in the first row or the quantile number 1, you will see 4 over 659 will give you 0.0026. The response fraction is very low. So in contrast, the quantile number 10, you will see 0.346, which indicates 34% of your rows qualified under quantile 10 will give you positive result, which are actually the true positives. And the bucket precision, so we can also compute how many qualified under. So the say like if you say 550 or divided by 652 will be your the bucket precision. So it will be 82%. So the response fraction will give you the recall for each bucket. The recall will be out of the total responses, which is 1561, how many of them in each bucket. So 34% in bucket 10, 24% in bucket 9, 16% in bucket 8, 12% in bucket 7, right? So if we go up, so you will see like small number of fraction from the total responses you had. In the last column, in the precision column, will tell you the records qualified under this quantile, how many of them are good. Because the true positive is 540 and total number of records qualified is 652, which will give you the 82%. So in this case, you will find the precision versus the precision is the one we got from the model result, and the mean probability. So they should go parallel, means like they should go they should have like a positive correlation. Should be the correlation coefficient should be close to 1. They should follow a line in ideal situation, but sometimes it will fall off from the line, but you should be able to track it. So if you track the mean probability versus the bucket precision following a line, as you see in the left side plot, your model is performing good. Now, so far we discussed about binary classifiers, how you can evaluate binary classifiers. Now let's look at how you can use confirmation matrix and the metrics you should be able to evaluate classifiers. How you can use them to evaluate multi-class classifiers. So in this example we discussed earlier, you should be able to predict which fruit class this fruit is belong to. So if you given a fruit, so your model should predict either it's apple, pineapple, strawberry, or banana. So you can only have those 4 in this world, in the hypothetical world. So say like you give apple, so the predicted value your model gives you apple. If you give pineapple, predicted value your model should give you pineapple. But in some situation, if your model is not a perfect, which is a real situation, so the apple, if you give an apple, probably your model will predict as strawberry, right? So this should be expected. So we had this table before as well, we discussed. So if you tabulate this as in terms of the conversion matrix, so you will get the matrix as in this slide. Here what I highlighted in red are off diagonal elements. which are false results on incorrect result. We should expect, in an ideal situation, we should expect all values should be on the diagonal in this confusion matrix, but the actual situation is not. In this example, you have like 4 different fruit varieties, and each we have like 50 of each kind, and we have 2000 samples we examine under this model. And out of the fixed 50 apple, we get 48 of them correctly identified, which is true positive, and pineapple is 45, strawberry is 46, and banana is 49. We get in the diagram, right? So then we can consider this one to calculate precision. So in this example, we are going to use one versus all case. So which makes we think, okay, if we take the apple as the classifier, which we get apple or non-apple. So the 48, the number 48 will be our true positive, as you see in the right side plot. For that, under that classifier definition, so all values in the predicted column apple, then the true positive value will be your false positive. So which makes in the red circle 1 in the apple predicted column will be sum to the count 3, right? So similar to that, in the pineapple, the predicted column pineapple, you have 45 as your true positive, right? In the confusion matrix, I mentioned everything in diagonal is true predictions. In the pineapple column, 45 is your true positive, and the red circle one in the same column, 1, 2, 1, 1 will be sum to 4, which is your false positive for pineapples. Similarly, for strawberry, 46 is your true positive, and you will have another 4 in the strawberry predicted column as false positive. So false positive, if I wanted to recall your memory, you say it is strawberry from your model, but they are not actually strawberries. Could be any other fruit. That's your false positive for strawberry. For banana, you have 49 out of 50 bananas you got identified correct, which is true positive, and you get another fruit classified as banana as a false positive. So you get only false positive for banana. For this model, the banana prediction is relatively good compared to other classes. So then let's look at, so we know all sample size is 50 for each class, and that we can have the third column in the right table you have. And the last column in the table is precision. For apple, how we can get the precision is true positive divided by true positive plus false positive, which will gives you 0.94. For pineapple, the precision will get you 0.92. If you wanted to recall the equation for precision, please go to the previous slide with our precision definition. I will try to add it here as well. For the pineapple is 0.92 as your precision. For strawberry is also 0.92. And for banana, the precision is higher, is 0.98. So this is what we can get as the precision if we consider one versus all type of classifiers. So now let's look at, in multi-class classifiers, we can look at the metric in average, in micro, macro, and weighted averages. So let's look at how we can do this with the precision. So first of all, let's understand what is micro, macro, and weighted averages. So in micro average values in a metric, all samples equally contribute to the metric. In macro average, all classes are equally contribute to the metric. Under weighted average, contribution of each class weighted by its size. So let's apply this to our example. So in our example, we have like a well-distributed sample set. So we have equal number of apple, pineapple, strawberry, and banana in our sample. So therefore, the weighted contribution will be even. So therefore, you will see the effect of that in a short while. So let's compute the precision. If we compute the micro average, so we have altogether 188 is our precision, total number of true positive values, and total number of false positive values are 12. We already had discovered from the previous slide. And if you compute the micro average precision is 0.94. If you want to take the macro average, so we get precision of each and every class. So we precision for apple, precision for pineapple, like that. So we add them all up, so we get the average of the class, the precision of classes. Right, so you have to get the average precision of all 4 classes. First you need to compute the precision for individual classes, and then how we can get the weighted average precision. So you have to uh, average each precision, the precision of each class weighted by its sample size. Like I mentioned, this is a evenly distributed sample. So you have like same number of samples from each class. Therefore, you will not see any difference. So you see micro, macro, and weighted averages are the same in this example. But I want you to know like how you can compute these values if you wanted to do the micro, macro, and weighted average of the metric. Now let's look at a slightly different example. So in this example, we have imbalanced sample. So which makes you a different number of samples from each class. So let's look at the result. So with the same method, we get false positives and true positives from the confusion matrix, multi-class confusion matrix. So we can reconstruct the table on the right side. So we have altogether we have 70 apples in the sample. 53 of them are correctly identified as apple from our classifier, and 8 of them not 8 of the 70, 8 of the fruits in our sample are non-apples identified as apples as false positive. Similar to that, 19 out of 20 samples identified as true values, true case for the pineapple. In the predicted column you can see it. So one other fruit was falsely positive for pineapple, right? So we have like the one as the false positive count for pineapple. And for strawberries at this time, so 49 out of 50 identified as strawberries. Those are like true positive for strawberries. And for the strawberry classifier, there are no other fruit falsely identified as strawberry. So the strawberry classifier worked really good in this case. Okay, so now let's examine same as banana. You will see 54 true positive and 16 as true false positive. If you count all of the true positive and false positive at this time, we had 175 true positives out of 200 and 25 false positive out of 200. So this 25 number should match to all the items counted under off diagonal cells, off diagonal elements. And 175 should be on the diagonal of the confusion matrix. That's another thing you have to note here. So now let's look at the precision column. So in the precision column, we get 0.87 for apple, which is 87% precision, and the 0.95 for pineapple, and strawberry is a perfect classifier in this case, got like 1.0 or 100%. Banana is the worst classifier in this case, is 0.77 or 77%. So that's your precision column. Now, when we compute the precision for this multi-class classification problem for imbalanced sample, so we get for the micro average precision is 0.898, so which is 175 divided by 200, and the macro average precision, which is like the precision you get all four precision for all 4 classes added together divided by number of classes will give you 0.898, which you get the same value. And then the weighted average precision is slightly different, so you get 0.881, right? Because it will take the weighted contribution, or the higher the number of samples present in this data set will contribute more from its precision, and lower the number of samples will contribute less from their precision into the weighted average precision computation. So far we discussed how we can compute evaluation metrics for classifiers. We discussed how we can get the performance for binary classifiers in detail, as well as how we can get for the multi-class classifiers. We discovered several methods and with examples, some good model cases and bad model cases, and some of the consideration you need to think whether I should use this metric or that matrix, and what are the implications. So we discussed those in detail. So now let's look at the other machine learning model type, regression models. In regression models, we all know we are predicting a numeric value. In contrast, the classifiers, we are predicting a class. So since we are predicting a numeric value, the evaluation criteria or evaluation methods or metrics will be simpler than the classifier methods. So you will have very few here I'm going to discuss, but you can find more. The usage is simpler than the classifier methods. The first one is mean absolute error, and then mean squared error, root mean squared error, coefficient of determination or squared, we are commonly known as the goodness of fit. Before we start discussing regression model evaluation, let's recall or let's revisit one of our problem worked in the class. I hope you all remember the Python exercise we went through, how we can predict miles per gallon of a car using its characteristics such as cylinder count, weight, time to accelerate, and then the displacement, horsepower, and model year. So you had the data set and you did some exploratory data analysis, you created variables, right? You identified the features, what are X variables for features, and what is your Y variable, which is miles per gallon, and then build the model, and then we predicted and we also evaluated this prediction results. Right? If you remember correct, we went through certain metrics we will be discussing in this lesson as well. So in very high level, what we predicted, or what is our Y variable, was the miles per gallon. So which is our Y variable, and what we predict is the same value from our regression model. So miles per gallon we are predicting. In the data set, we had the actual value collected by someone. So now our goal is to compare, similar to the classifier, we wanted to compare the actual value or the ground truth with the predicted value, like you see in the table right side of this slide. So miles per gallon was actually 18. Our model predicted 17.2. So the second row you have actual value of 17. Our model predicted 18. The third one you get miles per gallon 22. Our model predicted 21.6. So in this exercise we used a linear regression model to build this machine learning model, and we have actual and predicted value columns, so we can easily compute the differences between those two columns. So let's examine in detail how we can do this comparison. Now focus on the top right corner. You have the table, same table we had in the previous slide, but we have a new column added, which is called residual. In a residual column, what we do is we subtract the actual value, or so the subtract predicted value from the actual value. So y minus y hat in this equation you see on the slide. So 18 minus 17.2 will give you 0.8, and 17 minus 18 will give you -1. So like that, so we can get the actual value minus predicted value is your residual value. So what essentially that tells you. So let's think of this problem as like a two variable problem. So you have like X and Y variable in this regression problem, just assume for now. So you have 1, 2, and 3 are actual data points, and the orange line is your linear regression curve, which is a linear fit for those actual data points. And you see the regression is an indicator of how the actual value is deviate from the linear fit, right? So you see D2 and D1 is the same because the point is already on the line. So D2, D1, you don't need to have any value, it's 0. And the second point you will have the D2. You should be able to compute the distance from your point to the linear fit along y-axis. So the residual will tell you along the y-axis what is the distance it should cover the point when it's going to reach the linear fit. Right. In other words, you can find another one. So the residual sum of squares. So what you can do is you can get these differences or d values or the residual values. You can square each value. You already saw like we can get negative and positive values. So you can make it all positive values by taking square value of all the residual values and sum of them. Residual sum of square will be another term you can also analyze. And then also explain sum of squares will be another term you can use, which is your predicted value minus the average value. So the second term in the slide, the y hat minus y bar is the mean or average value. So you get that difference and square them up, and then you can sum all the values. So that will be explain sum of squares. The third term you can generate is total sum of squares, which will be your actual value minus your mean value. So how your actual value deviate from the mean value. You see the blue line on the top diagram or the plot in top of the slide. So that will tell you the mean value and how your each value is going to be deviate from the mean value. And you take the difference, square it, and sum all the values. That is total sum of squares. The coefficient of determination, we already saw this term in our previous slide, is one way of measuring the goodness of your fit. So how we can get that is R square is residual sum of squares divided by total sum of squares. So you can get the coefficient of determination using this method. And also in some analysis, what you can do is you can analyze the residual plot. So you can plot your predicted value, so your residual value against the predicted value, and you can see if any patterns are emerging out or if the data distribution is random. Then you can make a determination whether your fit is going well or not. This is this discussion is part of some other time. I'm going to cover in a very high level and very basic level. Therefore, I'm leaving this discussion out from this lesson. But I wanted to get you introduced to residual plot, also a tool you can use to visualize how good is your fit in regression problems. So now let's evaluate or let's look at that each and every metric I mentioned above and their definitions when evaluating regression models. The first one is mean absolute error. So in mean absolute error, what we will essentially doing is we are taking the residual value and take the absolute value. So y minus y hat. Take the absolute value and sum them up and divide by total number of observation or total number of samples in our data set. Right? So we divide by an n, assuming n is the total number of samples in our data set. So the mean absolute error, the value you can take from 0 to infinity. So because it's a positive number, you cannot take negative value because you are already taking absolute value. And the mean absolute error is the same, the value of mean absolute error is in the same unit. This is important as the predicted value. So if the predicted value, if you are measuring dollars, the predicted value is in dollars. So what is your mean absolute error values also in dollars. So the second metric you can use is mean squared error. So in mean squared error, what you are doing is you are taking the residual value and you are squaring them, and it's sum of squares basically, and divide by total number of observation or total number of samples in your data set. So mean square error has the so will be highly weight on larger errors. So we will discuss in the next one. So in the mean squared error is not in the same unit as your y variable. So you have to keep that in mind. If you want to take into the same unit, because you are squaring it, it will not be in the same unit. But if you want to take it back, so you can take the square root of it. So square root of mean squared error we call root mean squared error. Root mean square error and the mean squared error also a value you should expect between 0 to infinity. In root mean square error, it should be in the same unit as the predicted value. So I hope you are clear that idea. Okay. The goal of both mean absolute error and root mean square error is to get this value to 0. You will not get the exact 0 in reality, but you should try to get it closer to 0. So less error is better than your model. So the root mean squared error is insensitive to the direction of error, so which is the same situation for mean absolute error. It cannot tell you which direction of your actual value is deviating from the predicted value, right? So it cannot say whether it's a positive direction or the negative direction. And also, like I said about the mean squared error, since we are taking the square root, it put higher weight on larger errors. This is a debatable thing, but some people say this is a good metric. Some people against, but depending on the usage, so this should be okay at use for regression models. And then another important thing about root mean square error, this is a differentiable metric, so you can differentiate. So this you can use for many other things in your analysis. So the coefficient of determination or squared, we already looked at it earlier. So which you already have it. The goodness of fit will be 1 minus the sum of squares divided by sum of total, right? So we look at it earlier. And the expected value for r squared should be a value between 0 and 1. Higher the value is better your fit. Lower the value is worse in your fit, right? So in contrast to other three metrics, so the higher value will give you the better fit, and lower value is an indicator for a very bad fit, right? So the goal for r square is to take r square value to 1, right? So that's a perfect fit. You should get a value like say like 0 0.8, 0 0.95, 0 0.9. So those like we consider as good. If you take value like 0 0.35, 0 0.5, 0 0.4, which is an indicator your model or your fit is not good. If you say value is 0, that is an indicator saying you are predicting just the mean value of your data set. Right? So you are not doing anything better than that. All right, I hope you are clear with these 4 different ways of evaluating of these 4 different metrics you can use to evaluate regression models, and hope you can use these techniques in your exercises or any other machine learning application you will be doing in the future. So now let's look at in detail the coefficient of determination with an example. In this plot, 3 different plots I have 3 different data sets with different distribution of the values from xy variables. Right. So let's assume this is like a linear regression problem. You are predicting y value given the x value. So single variable linear regression problem. So the first case is a perfect case. You have r square is 1. All data points on the line, the predicted line, right? So in the second plot, at the middle of the screen, you will see some points are on the line, but other points are close to the line, but slightly deviated from the line. So you will get r square is 0.9 in this case, right? So when you have your data points are deviating further from the line, you get a lower r square, and when you get it closer, you get a higher r square. So in this case, you get the 0.9. The third plot, to the right side of your slide, is having no points on the line, but all other points also deviated from the line. It looks like, and they are scattered here and there in the plot, but they are slightly following a line. It's not very clearly pronounced. So in this case, you get R square value as 0.42. So this is what you should expect in terms of R square value, and what is the relation between that and a good fit. Right? So you can visualize using this slide. I hope you get the idea what you should expect as your R squared value if your model is fitting good. Right? So in multi-dimensional data, if you have more than one variable present in your regression problem, probably it will not be easy to visualize this in a plot or in any visual, but you should think that the lower the R value is the worst your fit, and higher the R value is better your fit. That is the end to our discussion on evaluating regression and classification models. So we did a detailed discussion on both of the techniques and how we can use different evaluation methods to evaluate the models. And I hope now you have a better understanding on the model evaluation and how you can use them. Most of all, like why we are using them. And this slide, I wanted to give you like a quick summary or the quick takeaways you can get from this lesson. The first one is evaluation is important to know how good or bad your model performs. We all discussed that in detail, so you should revisit our discussion and make sure you understand it correct. And evaluation results are used as a measure to tune the model. So your evaluation results will be continuously be useful, and you need to do this every time when you make a change to your model and to see whether your model is performing better or worse from the previous attempt. Right? And the very important thing, no training data should be used for testing, evaluating, or vice versa. Right? So training and testing data should be kept separate. You cannot interchange them. And also another important thing, no one metric fits all. So you have to use the metric which is most appropriate for your business use case, for your business objective, and also the algorithm or the machine learning method you will be using to solve the other problem. That's why this lesson is all about, to give you a better understanding on that concept. So it is important to have a good understanding on data and machine learning problem when choosing the evaluation metric, right? So like no metric fit all, but which one to choose is a decision you should make very carefully. You should have a better understanding on your data. What is your Y variable? What is the problem you are going to solve and how you are going to solve? So depending on that, you need to make the decision which metric you should be using. Evaluation metric need to align with the business use case and the business objective. You cannot evaluate using a method or metric you think of, but if they are not aligned with the business use case or the business objective, then your evaluation will not be helpful to serve your model in the actual application. The last point is evaluation results should be a part of the final ML product. You should deliver or you should preserve your evaluation results with all other information. We discussed that in detail for future use, and also it will be part of your deliverable or the product. So you should always tie with the documentation, and everything should be well documented, and you should have ability to reproduce your model given this documentation or and the data set to someone. So the machine learning model should be reproducible. Otherwise, it's not a magic. So you have to reproduce using the same conditions, using same data. So that's how we can ensure our machine learning models will be better serving in the application we intended to use it. Okay, so this is the end of the lesson. I hope you get a better understanding now on this topic on evaluating machine learning models, and we will discuss more concepts about the machine learning model building life cycle in the coming lectures. Thank you.